I'm not going to draw the entire study. I'm not going to draw the bookshelf and perspective and all that fun stuff. Right? But and on this table is a bottle full of quinine sulfate, also known as tonic water. You can go buy this like at Market or HEB, right? And he's sitting in the study, and he's got a glass of white wine that he's drinking, that his butler probably poured for him. It's yellow right now for some reason, right? This is white wine. And he happened to be looking through it with his eyeball, which was the original photo detector. So he's looking at the bottle. And he was sitting there drinking his wine, whatever, and he had a stained glass window in his study. And at the right time of day, I'm going to draw the sun like I did when I was, in pre-K, like a squished spider, right? The sun was out. And that ray of light came through the stained glass window, hit this sample, and he saw a little glowing ball of light on the inside of the glass, on the inside of the liquid, right? Looks through his wine glass, he sees it, he's like, that's new. That was the beauty of science back then. You kind of just did anything, right? You put a voltage on a frog, and the muscle twitches, you're like, I bet electrical impulses are important in motor function, right? Boom, right? That was Galvani, by the way, of whom we named the galvanic effect. So what we have is a light source, the sun, which was the OG light source. And then we had a stained glass window. What do you know about stained glass windows? How many of you have ever seen a stained glass window before? How would you, what are some properties of a stained glass window besides the fact that it's a window? It's colored because the glass is stained. Dun, 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 right? It's got a color to it, which means it's probably absorbing some wavelengths and transmitting others, right? So it's a wavelength filter. So we have all the blocks. We have light source. We have a wavelength selector. Now, it's fixed. It's like an interference filter in this case, right? You don't get to pick. I'm sure that Stokes, even though he was wealthy and had nothing to do with it, did not have a battery of stained glass windows that his butler changed out for him. He had a sample. And then, how many of you have ever had wine before? Or seen wine before? Is it clear and colorless or clear and colored? Clear and colored. So wouldn't you argue that it's absorbing some wavelengths and transmitting others? Like a filter. So we have another wavelength selector. And importantly, it's a different wavelength. So the first wavelength selector picks the excitation light. And remember, fluorescence changes wavelength, right? Energy is lost. So you need something to select the second wavelength. In part, to just isolate that wavelength, and also to block the excitation light, which is much more intense. And then a detector. Something that converts optical input into electrical impulse that we can then process, right? The difference between the observation, by the way, and the light, these two are not in a straight line. There's about a 90-degree arc between the beam of light from the sun and the observation. You don't normally look in the excitation direction, even with a detector. It doesn't change very much, right, since then. It's an ingenious experiment. And 1 year, the student raises his hand in the front. He's like, how the hell did Stokes come up with this idea? Like, was he sitting there high on opium? Like, I'm going to, no. He was literally sitting in his study, drinking wine, probably looking at a bank tally of the money coming in from his various exploits of other people around the world. And was like, huh. And I will tell you now, right, as scientists, that moment, that moment, is what separates scientists from non-scientists and good scientists from bad scientists. Because a bad scientist or non-scientist would look at it and go, that's weird. Or gone like, witchcraft, right? But it's the devil. I've isolated evil in a jar, right? Mass hysteria ensues. People are burned at the stake. A good scientist goes, I'm going to put something else in there and see if the same thing happens, right? And it didn't. So he put his quinine sulfate back, his tonic water back, and lo and behold, it was fluorescence. He came up with that word, right, at that moment. A good scientist at DuPont had a reaction go bad, came back and said, huh, this stuff is really, really, really slippery and adheres to nothing. I shall call it Teflon, right? At North Carolina Chapel Hill, an organic chemistry reaction went awry, and they threw it out in the trash pile in the back of the building, like they used to do in the late 1800s. And it rained, and it caught fire and burned everything to the ground, right, in the vicinity. And they went, huh, that could be useful. It's called acetylene, by the way, right? Good science happens when something inexplicable occurs. Think about penicillin, right? How was penicillin discovered? Right? It was someone got some mold on some petri dishes, basically, right? And bacteria didn't grow. And a bad scientist would have gone, let's throw them out. And the good scientist is like, I wonder what kept those bacteria from growing. Put it in me, right? So this is one of those moments where someone asked the right question and followed up on it, and now we have an entire technique, right? Because let's look at today. If we were building the same experiment, right? Sorry to get a little philosophical, but it's important to understand. Many of you, at some point in your lives, whether, like, Ardo, what do you want to do when you grow up? What's your plan? You have no idea. That's okay. Anyone else? Anyone have a plan? Misty, what do you want to do? Medicine? Of some kind, right? So you get some weird lab result for your patient, and you're like, huh, that's weird. Let's have lunch. No, right? You're going to follow up and figure out what's going wrong, right? I mean, I would hope so. If not, I'm not going to see you as a doctor, right? I keep track, by the way, of all my really bad students. Misty's not one of them. That way, like mentally, that way if I'm dying like of a heart attack in 10 years, and just kind of pick on somebody like Michaela, who's not a bad student, and Michaela comes in, let's say she got a D in my class, I'd be like, nope, I'll wait for another cardiothoracic surgeon. I'm good. I'm just gonna clutch my chest in pain until because she got a D in my class. You know, I remember these things, right? And that's why when you come to my office in the semester, you're like, can I do anything for an A? I'm like, for a B or C? I'm like, no, because I don't want you to operate on me later, right? Not till you master fluorescence as a modern experiment. So nowadays, we still have a light source, but we don't use the sun. We use either typically lamps, high intensity lamps, or lasers, or LEDs, the three L's. Lasers being the most sensitive because they offer the most power, right? But we don't always. Actually, to give you perspective, when I started doing fluorescence at Texas Tech in my labs, we use lasers on all microscopes. I just got a sweet new microscope this past year. It's like a space station as far as complexity goes. It's amazing, and it's got this ridiculously powerful LED light engine instead that we use. So it's much cheaper, more compact, more efficient. But that light source puts out many wavelengths typically, so we need a wavelength selection. We're either going to use an interference filter if we want a fixed wavelength, or monochromator. That monochromator will typically be short focal length. So we're tying all these concepts together. When I say it's a short focal length monochromator, what does a short focal length monochromator mean? What does that mean to you if I say the focal length is short? But thank you. Yes, one thing is that the intensity, the throughput of light is high. I need a lot of power for fluorescence, right? So I'm going to use a short focal length monochromator because I want a lot of power. Also, I don't really care about the wavelength because if I may scroll up for a second, I'm sorry. If I've got this broad band of absorbance here, that's like 50 nanometers wide, and my band pass on my monochromator is 5 nanometers wide, that's totally fine. Right? I'm still more narrow than, as long as my light falls within the absorbance band, I'm good. Right? So I will sacrifice spectral resolution because I don't need it because I want power. Okay. Then I've got a sample, which is typically a cuvette, not always though. And unless you're doing microscopy, where you're taking images to do in my lab, we will measure at 90 degrees, right? And I'll tell you why in a minute. We have another wavelength selection. Again, either an interference filter or a monochromator. By the way, someone on Zoom is unmuted. I just want to let you know before something catastrophic happens for you and hilarious for us. This will be a longer focal length instrument. Not super long, but longer than the excitation monochromator. So we have an excitation monochromator that says excitation, and this is my emission monochromator. I need a little bit higher resolution, so I sacrifice some power in this case, right? Then after this, I've got a detector, and I have two choices, really. If I'm scanning or fixed wavelength, or like one, fixed wavelength, I'll use a photomultiplier tube, or PMT. I could also use an avalanche photodiode. Or if I'm acquiring the whole spectrum at once in one shot, or I'm doing imaging, one of the two. So I'll use a CCD array, right? Those are my detector options. A little more sophisticated than a stained glass window and a glass of wine. But from an operation standpoint, it's the exact same experiment, right? You may notice as you go through my exams. By the way, I finished the answer key yesterday for like the next set of exam questions, and inexplicably, 3 exams worth of answers hasn't saved, and I'm waiting for it to magically appear before I redo it. I was so pissed last night. I was uploading it to Blackboard. I'm like, wait a minute, why are 3 pages of my work blank? So I'm hoping that like magically my cloud updates my changes. Otherwise, I'll just redo it. It'll be up tonight. But I like to ask questions about this, like the parallels, right? What are the parallels between the experiment in 1880, whatever, and 2021, right? Like, what is the analog of a CCD camera in his time, Stokes' time? It's the eye, right? What's the analog of the excitation filter today? It's the stained glass window, right? And so just think about it, right? It's important to know. So why do we measure at 90 degrees? The reason we measure at 90 degrees is to minimize scatter. I need to draw something to explain this to you. So scatter is not isotropic. Isotropic emission is emission that occurs randomly in time and space, truly random. So if I had a point source, a point matter that emitted light randomly in space, what would the distribution of that light look like to you, probably, as a function of 3D angle or solid angle? I have a point, and think about light as a vector, right? If it can emit light in any direction, randomly, with equal probability, what is the distribution of intensity around that point, probably? It's spherical. Yeah, absolutely. It's absolutely spherical. The sun is a good example. If the sun was not isotropic, we wouldn't just have seasons because of axial tilt. We'd have points on the year cycle where temperature was scorching and all life on Earth died, and then temperatures where everything froze into solid water, right? Not good. So scatter, fluorescence, and other things like that are random, but scatter is not. So scatter, if I was drawing like a vector, like this is my light direction, and this is my scattering object, like a molecule in my solution, which would be Rayleigh scatter, or maybe like a dust particle in my solution, which would be called ME scatter, MIE. There's different kinds of scatter, there's not different size. When that light strikes that surface, fluorescence is emitted in every direction. Okay. I'm going to try to draw a sphere as best as possible. The spherical distribution because it's isotropic. Scatter, however, has a lobed distribution that looks like this. Scattered light, let's draw this in 3 dimensions, has a peanut-shaped distribution, whereas fluorescence has a spherical distribution. So it turns out, just happenstance, that scatter is largest in the forward direction and in the reverse direction, and it's equally intense in both. So if you're observing the beam as it's coming at you, which would be not great anyway for fluorescence, or looking in the reverse, which is called backscatter, you would have more scattered light. 90 degrees happens to be 90 degrees from the optical axis happens to be the point where scatter is the least. But for fluorescence, it's always the same, so we don't lose anything by changing our angle of observation for fluorescence. Or fluorescence stays the same, but we reduce our light scatter. Even though the light scatter is of a different wavelength, the excitation power coming into the sample is always larger than the fluorescence light that I can collect out of it. Right? So that scatter, while compared to its excitation being insignificant, actually can cause a significant background, right? Whether it's just an offset value or it has noise associated with it also. It's just light I don't want to detect. So by measuring 90 degrees, I minimize scatter, okay? And that's why. When we talk about measuring scatter later on, we actually don't want to measure at 90 degrees because that's the worst case scenario, right? So the last thing I want to introduce right now, we just covered instrumentation entirely, is a neat little technique in fluorescence. So fluorescence, as I mentioned before, is sensitive to the environment around it. It's not like absorbance. Absorbance is instantaneous. So there's no time to react. The local environment is meaningless. But after absorption occurs, the molecule reorients itself in the excited state before it emits light. So the solvation of that molecule matters. The ionic strength of the solution matters. Other nearby things that can cause external conversion or quenching matter, okay? So there's a technique called Forster resonance energy transfer. Or FRET for short. It used to be called fluorescence resonance energy transfer, and they decided to rename it after the person who discovered it. It's Forster. This is sometimes it's called a spectroscopic ruler. I'm going to get really crude. I'm very sorry. I just thought of this analogy. It may be a totally horrible analogy. What is the one surefire way, if you have a couple, let's say for argument's sake, it has to be a couple capable of producing offspring. Okay, just in this case, so you have a heterosexual couple. What is the one surefire thing that would let you know that those two people copulated, use the SAT word? What's the one thing that it would prove, the undeniable proof that two people got busy at some point in the past? A child, pregnant, right? The ultimate interaction. Because you could have all the kind of speculation you want. Y'all, when I was in college, my chem major friends had a betting pool about whether another friend and I were exchanging information of a genetic variety. I was very pissed. That's a very sexist and pig-headed thing to do, right? I found out about it when I was very angry. What the hell, guys? If you're that curious, ask, and I'm not going to tell you anyway, but why have a betting pool? And again, how does one prove that you won? Unless I come out or the other person says, yes, right, on these days, or whatever, right? It was the dumbest thing ever. I was so angry that I was this topic. But like, a baby is perfect proof. You know something happened, right? So, and the reason is because material's been exchanged, right? And there's like obviously a change in one of the two participants, correct? Ladies have to do all the work, man. You're just accessories and therefore the problem. All right. So if I've got a molecule, and I'll call this molecule a donor molecule. Here it is, floating around. And I excite it with a wavelength of its excitation that it wants to absorb, right? It will emit fluorescence on its own, okay? So if I was plotting that, if I had like wavelength and intensity here,
and then it just sits there and doesn't let me in.
I get fluorescence, or signal. This is my donor fluorescence. Sorry, I need to spell fluorescence properly. Just a point of pride here. All right, and while I'm at it, I'm going to make this actually color-coded. Here's my donor absorption.
I think I was going to have to wait.
And let's say my wavelength I'm using is right here, right? Now, let's say I've got an acceptor molecule also nearby. It's a different molecule.
Maybe next time I'll just spam it all at once and stuff.
I'm saying ACC, so you don't use it with absorption, but just use A. And when it's far away right now, far away in molecular scale, right? It could be like 3 molecule lengths over, possibly, right? It has its own absorbance. That matches or overlaps strongly with the donor fluorescence. In other words, that molecule, the acceptor molecule, can absorb the light emitted by the donor molecule. Okay, it's like the fluorescence coming off the donor matches the absorbance of that acceptor molecule. When they're far away, that wavelength of excitation does not do anything. You can see that wavelength of excitation is far away from the donor absorption, right? So nothing happens to the donor molecule. So if I was looking at my sample and these two are far away, I would see fluorescence from my donor and no fluorescence from my acceptor. But if I can drag this. Yep, I can. Sweet. All right. Now let's do this though. Let's get these two molecules closer together. Now they're close. How close? A few angstroms. Right? Now, what happens is what's called forced or quenching. The donor molecule does not actually emit light when they're close together. You actually get coupling of the energy levels through dipole-dipole coupling, and you get energy transfer. So a photon is not emitted, but rather the energy that the donor's about to absorb, about to fluoresce, matches the energy that the acceptor needs, right? So it just transfers over, because it's just the coupling of electric fields, right? And now what I get, instead of, I don't get donor fluorescence anymore. Instead what I get is acceptor fluorescence. So what happens spectrally is that this signal goes to 0. I still am only exciting the donor, but instead I get acceptor fluorescence. So yes. It will be, yes. Because your donor absorbance is shorter wavelength than the donor fluorescence, right? And donor fluorescence matches the acceptor absorption. I know it's getting a little confusing, right? Which means that you have even further wavelength. So, for example, if I'm exciting in a blue region, for example, like 450, let's say, right in the middle of the blue region, and I've got a green fluorescent protein, and it's getting close to a yellow fluorescent protein. Well, yellow fluorescent proteins absorb green light and emit yellow light. So I have one excitation source in this case, right? I'm exciting the donor only. I don't excite the acceptor. And so when those molecules are far apart from each other, I don't have fluorescence from the acceptor. When they get close to each other, I can't see them get that close, right? I can't resolve that. But by measuring spectroscopically, I know they got together and got busy, so to speak, right? I wasn't there, nor should I have been, when a pregnant couple got busy. Yet I know they did, because the person's visibly pregnant, right? That's a really crude analogy, but I'm going with it today, right? We're going to stop there. We'll talk more about FRET. This is, by the way a lot of molecular interaction has been discovered over the years, like how we know protein X works with protein Y in your body to do a job, right? So it's pretty powerful. So I'll see you all on Wednesday.
Dr. Pappas?
Yes.
I know that we have a meeting at 2 today.
Yes.
But I've been canceling this appointment with a doctor for the last 2 weeks, and I think I kind of pissed them off. Because they.
You want to meet tomorrow?
Yeah. Can that happen?
Are you free at 10 tomorrow?
Yeah, I'll be free at 10. I just feel bad
Yeah.
because I keep missing, and then they called me Friday to
No,
change
no,
the whole
it's
thing?
totally fine. That actually works out for me just fine. So I'll tell you what. Come. You want to meet virtually or in person?
We can do in person because I want to bring you my notes and stuff and see
Yeah, yeah.
what
So
am I
let's
missing.
talk at let's yeah. Come by my office at 10 tomorrow.
Okay, thank you.
All right. Thank you. Bye.
Bye. way. No way.